So we're going to continue with our discussion on interference. So interestingly enough, when people were originally looking at interference of light kind of problems, they were not doing this correctly because they were using separate light sources. So think about a lamp, right? A lamp is not producing a continuous train of waves. It's producing actually a series of short trains, and the phase difference between one train and the next train is actually random. So if you are mixing light from two separate sources, there's no continuing relationship between the phases. You don't have a coherent source of waves, and you just get like a quote unquote average brightness. So to successfully demonstrate interference, we need, first of all, we need a light from a monochromatic source. So it cannot be like a regular bulb. It has to be a monochromatic source of light. And what this physicist named Young came up with was, this is called Young's double slit experiment. And the experiment goes a little bit like this. So he had a monochromatic light source, right? So we'll call this monochromatic light source. And from this light source, he said, first I'll set up the first slit, right? So that, as you can imagine, in this first slit, diffraction is going to happen, right? And the waves start spreading out like this from here. And he then had, oops, I beg your pardon, he had two slits at this point. You have one here. So that's what it looked like. He's got one slit here, one slit there. So these waves approach this point here, right? And now you have one wave coming from here, and then you have another set of waves, emanating from that point on, right? So essentially they're interfering with each other in this zone right here. So drawing this in a slightly different way, I'm going to draw it like this instead. So you have the first slit, and you're going to have the monochromatic source here, and you're going to have, sorry, I'm going to just draw a line here so you can see it's separate. You have the first slit, and then you have your second slit. And what Young also did was he put a screen up here, kind of out a little bit farther away, to capture whatever the pattern of light was being produced, right? So what he found was, and just this is the important parameter here, this gap between the two slits, that is called, this denoted by the letter A, that the length of the gap, right? So what he found was, well, light from here has to kind of travel up to here, let's say, right? But there's going to be a portion of this wave that's going to make its way to the same point out there. So essentially, and this distance, we'll call that D, from the slit to the screen. And that's our screen right there. So what he found was, there are two parts of this wave that are traveling slightly different distances. And what he ended up finding was, if you measure from kind of like here, from the center point of this slit, this distance is x. Now, the wavelength of the light is very short, right? And in this case, we're talking about light, so the electromagnetic interference, electromagnetic wave, I beg your pardon. So what is the wavelength of light? It's like 10 to the minus 7 meters. So what we have found experimentally is that the slits must be less than 1 millimeter. This is what we were talking about earlier when I was asking you to go and look at a straight light. And what we also found was the distance D must be a bit large. It should be like a meter. So here I've just kind of summarized the points we were just referring to: A less than a millimeter and D about a meter long. So I want you to just take a note of this diagram though. There's this quantity X. What is X? I said it's basically like, the distance from the middle of the slit up to this point, but why that point? What are we talking about there? So let's actually take a look at what the interference pattern would look like on the screen. You were looking at the screen kind of front on, not from the top down as in the previous picture, but if you're actually, you were the wave, let's say, and you're looking at the screen, and the source of the light was green, for example, monochromatic green. This is kind of the pattern what you would see, essentially, right? You're going to see some green blobs produced by the constructive interference from of the wave from the two slits. But in between them, you're going to see these dark patches of the screen that are not illuminated at all. So that is what X is referring to. Oh, I beg your pardon. X is referring to the distance between two fringes. So X is distance between fringes produced by constructive interference. And this also tells you why you have dark spots on the screen between the green bars. You have these black areas. That's the destructive interference part of the story. So what we have found is for constructive interference, you can kind of basically say, well, the wavelength of that light can be given by A times X divided by D. So X, remember, is the distance between the fringes, and A is the slit gap, the gap between the two slits, and D is the distance to the screen. So let's work through an example on this. So let us say light of the wavelength 490 nanometers, 590 nanometers is incident on a pair of narrow slits, and the interference pattern is observed from a screen, is observed in a screen that's 1.5 meters away. And I can clearly see 12 separate interference fringes that are spread out over a distance of 2.1 centimeters. So what is the separation between the slits? Well, the answer there is basically going to be very simple. It's going to be A equals lambda D upon X. So what is lambda? That's easy. We know it's 590 times 10 to the negative 9 meters. And what is D? D is, again, very straightforward. It's 1.5 meters divided by X. What is X? Well, remember, there's 12 fringes measured over 2.1 centimeters. I'm not gonna, it's better to measure the total distance of all the fringes rather than trying to measure individually, because the likelihood of not being accurate is quite high in that sense, right? So you are better off instead saying, well, I'll just go 2.1 centimeters, which is 0.021 meters, divided by 12. That is what my X is. So if you work all of that out, you're going to find that A is equal to 4 times e to the negative 10 meters. So that's about what? 0.05, about half a millimeter. That's basically what the opening of that length is, of that slit is. Note that the color of the light is dependent on its frequency. In general, for coherence, we expect a single frequency, therefore a single wavelength. In practice, if you're using white light, what is white light? It's a whole range of colors, right? So in practice, if you're using white light, you will observe a few colored fringes as the different wavelengths interfere constructively and destructively in different places. So it's better, for that reason, not to use white light, but to use a monochromatic source of light, or as close to monochromatic as you can get it. There's one last topic here to cover, and that's called diffraction gratings. So we looked at the case when we have two slits, right? And we create an interference pattern. What happens if you use more than two slits? Basically, what it's going to do is, your interference pattern is going to make the maxima, the constructive interference points. It'll make it sharper and brighter. So the more slits there are, the sharper and brighter the maxima become, and that makes it easier to measure the difference between these fringes. The problem is the multi-slit device is actually called a diffraction grating, which is rather confusing because it's not actually, you're not actually spreading the light, diffraction, you're not actually spreading the light for interference. It's actually an interference grating, but it's called a diffraction grating. So it's basically going to look a little bit like this. So it's a lot of these little teeny tiny, openings, and it's obviously not to scale, but imagine this is like, we're talking about openings that are millimeter or smaller, right? But it's a lot of these openings, and you have some kind of light that's incident on it. And again, I suggest a monochromatic source of light. And there's a screen right along the side here, right? And you're going to find that there is down here, we'll call this a central maximum, right? So there's going to be a fringe that will be the brightest fringe that you see. It's going to be a central maximum. But if you kind of count from left to right, you might have, you know, like a first maximum right there, and another first maximum down here, right? So what we find is that from, let's call the angle theta to the first maximum. So what we find is, if we derive the formula here, we get this really handy dandy equation which says n is basically the number of the maximum number of maximum. So the first maximum that you have here, n would be equal to 1 for that one. So you have the equation n times lambda, the wavelength of the light, is equal to d times sine theta. Oh, but hang on a second, guys. What's d? Well, this, guys, is d. So d is the distance between successive slits. The distance between the successive slits. So let's work through an example on this. So here's an example, guys. Assume you have a grating that has 5,000 lines per centimeter, and you are shining a monochromatic light on it that is 7.2 times 10 to the negative 7 meters. So what is the angle at which the first maximum is produced and the one that the second one is produced, second maximum is produced at? So the first thing we do is we try to calculate d, right? So d is going to be equal to 1 upon 5,000 centimeters, which is going to work out to be 2 times 10 to the negative 6 meters. So sine theta is equal to lambda n lambda upon d. I think we are all clear on that. So the same thing is going to apply here. What is lambda? Lambda is 7.2 times 10 to the negative 7, which is right here, and we have just calculated a d. So in this case here, n is equal to 1, and in this case n is equal to 2. So if you do the algebra on that and do an inverse sine, you're going to get that sine is equal to the theta here is equal to 21 degrees, and theta here is going to be equal to 46 degrees. So folks, that brings us to the end of the chapter on superposition. We will see you in the next video for chapter 16. Thank you very much.